This video is about perpendicular bisectors in triangles. So we want to start by discovering the definition of perpendicular bisector. I have drawn a segment AB, and I'm going to put a midpoint right in the center of it, and I'm going to call that point M. And that midpoint has divided AB into two equal segments. So AM is the same length as BM. Any line or segment that I now put through M could be called a bisector of AB. So this little guy is now a bisector of AB because it goes right through the midpoint of AB, cutting it into two equal pieces. That segment, however, is not a perpendicular bisector because it doesn't make a 90-degree angle with AB. So I'm going to get rid of that one and drag over this vertical line, which is a perpendicular bisector of AB. So it forms 90-degree angles with the segment AB, and it splits it into two congruent pieces. So this would be called a perpendicular bisector. It doesn't have to just be a segment, right? It could be a line that goes on forever as well. And it doesn't have to be cut in half itself. It just has to cut the original segment in half. So it splits AB into two equal pieces, and the perpendicular bisector itself could be a line, could be a segment. It doesn't have any determined length. There's a property of these, which is that anywhere I put a point along this perpendicular bisector, like let's say I put this point here and call it C, it is the exact same length away from A as it is from B on this picture. So C to B would be the same length as C to A, as long as that point C is located somewhere on the perpendicular bisector. So that's not the greatest picture, but let's write down that property on this next slide here. Any point that's on the perpendicular bisector is equidistant, which means equal distance, from the endpoints of the original segment. So here in this picture, C is up top, but it's equidistant from A and B, so that those two distances are going to be the same, because C is located on the perpendicular bisector, and anywhere that you put that point C, this property is going to hold true. So if we apply it to a question, in this picture, I know I have a perpendicular bisector because I can see the 90-degree angle. I can see that AC is being split in half because I have these two congruent signs, which means that BD is the perpendicular bisector of AC. Because BD is the perpendicular bisector of AC, that means any point on BD, for example, this point right here, is equidistant from the endpoints. So B to A would be equidistant with B to C. So those two segments are the same length. 4x is equal to 6x minus 10 because of the property we just learned about points that are on perpendicular bisectors. We can solve this equation for x and then use that value of x to answer the question. It wanted us to find the length of AB. Because AB is 4x, we can plug in the 5 and figure out that the length of AB is 20. And remember, when you write AB with no symbol above it, that means the length of. A totally different definition that's going to be applicable for the rest of these notes is that when three or more lines all intersect at the same point, then those lines are called concurrent lines, and the special intersection point is called a point of concurrency. So it's just a more specific way of saying that lines intersect. So rather than calling it just the intersection point, we can call these lines concurrent because there's more than three, there's three or more of them, and they all intersect at the same point, which is called the point of concurrency. But basically, they're intersecting lines, and this is the intersection point. We just want to say concurrent when it's three or more lines. The reason this is going to matter is because when we put perpendicular bisectors on a triangle, you should see a special property that involves concurrency. So we've got construct the perpendicular bisector of each side of this triangle. So I've got three sides of a triangle, which means I'm trying to construct three different perpendicular bisectors, and I'm going to do them in three different colors. I'm going to start with the bottom of this triangle because it's the easiest one. I can see the midpoint of the bottom of this triangle just using my eyes, right? This is equidistant from the left and from the right. It's right in the middle of the bottom of this triangle, and I want to draw a segment that goes right through that midpoint that's perpendicular to the bottom of this triangle. So it's basically this segment. I'm not going to continue that segment yet. Sorry, that came out a little messy. I'm just going to make that neater. Here's the midpoint, and here's the segment. And I'm going to continue that segment after I've drawn the sort of starter segment for the other sides as well. I'm going to go to the vertical side next. I can see where the midpoint of that is. and I'm going to draw the line that's perpendicular there through that side. So this, you kind of have to stretch your imagination a little, or actually physically bend your head or move the paper. If you want to imagine being perpendicular to that side, it would look like this. So now I have these two starter segments. The third one, it's a little harder to see the midpoint, so I'm actually going to calculate the midpoint by knowing that the two endpoints are, let's see, this point is located at 0, 1. This point is located at 6, 4. I'm going to find the two averages in order to calculate the midpoint. And 6 over 2 is going to be 3. 5 over 2 is 2.5. So I'm looking for the point at 3, 2.5, which is right there. Now this time I want to draw the segment that is perpendicular to the long side of this triangle. So I am going to tilt my head a little. Try to imagine that the hypotenuse of this triangle is like the bottom and B perpendicular to it. And it looks something like that. So I've drawn my 3 starter segments for my perpendicular bisectors. All 3 of those lines are completely different, right? But when I connect them, so if I connect the green one by extending it as far as possible, extend the blue one as far as possible, extend the red one as far as possible, you'll see that those lines that we just drew all are concurrent. They intersect at a point together. And this one would be called a point of concurrency. So when you draw the perpendicular bisectors of all 3 sides of any triangle, they're going to intersect at a point, which is a very special property. Oops. Forgot to say point of concurrency. I just said point of concurrency. That's a point of concurrency. So here's what we just learned. The property is that perpendicular bisectors of a triangle are concurrent at a point that is more specifically equidistant from the vertices of the triangle. I'm going to go back a slide so you can see what that means on this picture. This point that is in black that I just showed is the same distance, equidistant, from the 3 sides of this triangle. So this black point to this corner, to the 3 vertices, which means the corners of the triangle. Black point to this corner, black point to this corner, black point to this corner, those 3 distances would be the same. So that sort of puts together all the properties that we talked about in these notes. So here it is in a textbook picture, which is a little bit neater than mine. I've got 3 perpendicular bisectors, right? PY is one of them, PX is another one, and PZ is the other one. They all intersect each other right here at P, and that point P is the same distance from all 3 corners of the triangle. So P is the same distance away from C as it is from B, as it is from A. But of course that point P was found by constructing the 3 perpendicular bisectors. This point of concurrency has a special name. It is called the circumcenter of the triangle. So how do we form the circumcenter of the triangle? We construct the perpendicular bisector of each side and connect them. You'll find that they all intersect at the same point, and that point is called the circumcenter of the triangle. It has another very special property, which is that when you have the circumcenter of the triangle drawn, if you take out a compass, which is a geometry tool that makes a perfect circle, if you put the pin of the compass right on P, and then the pencil right on one of the corners of the triangle, like A right here, if you then draw the circle, it'll go right through each corner of the triangle and have P at the center. My circle is a little lumpy because I wasn't using a compass. But that's sort of a special point, right? P is the center of the circle that goes through each of the corners of the triangle. So in this case, it's like PA is a radius, and PC is a radius, and PB is a radius because, you know, the radius of a circle is the same the whole way around. Depending on the shape of the triangle, so whether it's acute or right or obtuse triangle to begin with, the circumcenter might be located either inside the triangle, like that point P we were just looking at. It might be located right on the triangle, as in a right triangle, which was the first example that we did together. Or if you have an obtuse triangle, that point of concurrency might actually be outside the triangle, but it still has that same property of being equidistant from the corners, so that each of these could be a radius for the circle that encompasses the triangle, like this. And then you might be asked to apply that. So let's say we want to find the coordinates of the circumcenter of this triangle. has corners at 0, 6, 0, 0, and 4, 0. So I'm going to put a point at 0, 0. See if it'll put a point here automatically for me. Oh, good, it did it. And I want to put a point at 0, 6, which is up at the top here. I don't know if it's going to do that. Oh, yeah. And 4, 0. All right, so I've got my 3 vertices. I could draw the triangle that connects them. Hope it lets me draw on this. It does. Good. Draw the triangle that connects them. So here's the triangle that I'm trying to create the circumcenter in. It's a right triangle, which means ultimately I'm looking for a point that's actually on the triangle, similar to the first one we did. So I'm going to start by finding 3 midpoints. Middle of the bottom, and then making a perpendicular bisector, my starter segment. I'm going to find the midpoint of the vertical side, which would be at 3, and then draw a perpendicular segment through there. And I'm going to find the midpoint of the sloped line there, the hypotenuse of this triangle, by doing the actual distance formula. So 0 plus 4, not the distance formula, sorry, the midpoint formula. 0 plus 4 divided by 2, and 6 plus 0 divided by 2. So the point I'm looking for is the point 2, 3, which is right here. And then draw a line that is perpendicular. That did not look perpendicular. I'll delete that one. That is perpendicular to the hypotenuse. And then when I extend these, I'll see where the green, the red, and the blue lines that I just made intersect each other. That really should have been a nicer line. And I'm looking for the point where these 3 perpendicular bisectors are concurrent. And there it is. And the coordinates of that point of concurrency are 2, 3. It just so happens to be that it's the midpoint of the hypotenuse. So we want to say, oh, maybe I shouldn't call it P since I already have P on this picture. I'll call that one C. And we'll say that the point C that we're looking for is 2, 3. Or the point of concurrency, the circumcenter, is 2, 3. And that is all.